Hi, this is the fifth video in the probability functions section on sampling distribution. Kind of the basic idea behind this is if we're testing out some assumptions that we've made. For instance, if we have an assumption that the average height, the mean height of students in a college is 1.6 meters, if you took a sample of one. And that student was 1.75 meters, 1.4 meters, or whatever. Would that disprove the assumption that the mean height was 1.6? Well, I think intuitively you'd say, well, on a basis of a sample of one, then really doesn't hold water. And what we tend to do is we would take a sample, a larger sample, maybe 50 students, take the mean of that. And decide whether or not that mean was sufficiently different from the 1.6 assumption for us to do something about our original assumption, discard it or replace it or whatever. Now, so the principle basically is what we do is we take a sample size and take the mean of it, and we use that as what is called our test statistic. Now, the maths behind this comes from something called the central limit theorem, which states that the distribution of sample means is the distribution. So the sample mean is in effect like a new random variable that we've created. The distribution of sample means approximates to a normal distribution as the sample size gets larger, regardless of the population's distribution. Sample sizes of equal to or greater than 30 are often considered for the central limit to hold. Okay, so if we've got some random variable with any distribution, could be a uniform distribution, for instance, with a mean of 20 and variance of 16. So X bar is the mean of 36 samples. So we're going to take this X bar, and we've got this, what is effectively a new random variable. It's being derived, but and we would expect the mean of that X bar to be equal to the mean of X. Okay, yeah, it is. There's maths that can show that. But I think we probably expect that because of the averaging process, that actually we're going to be getting a smaller variance. In fact, if we find that the sample size is n and n is large enough, then X bar approximates to a normal distribution with that original mean here and a variance here divided by the sample size. So the distribution of this X bar is known as the sampling distribution. Okay, and that's the central limit theorem. So we just have a look at this example here. So if we simulated distribution of means of uniform samples, so we're taking random samples from a uniform distribution, taking 50, and then we take their mean, and we've got that random variable. Okay, then we do that over and over and over again. So we keep getting different observations of this new random variable, and we plot them on a histogram. And what we get is something that looks like this. And yeah, it's got the same mean here, but obviously the variance, so standard deviation, is going to be sort of relatively tight. So that's what we've done here. And in this case, what we've got is a normal distribution, or virtually as near to normal distribution as we would need for most purposes, because we're taking 50, which is quite a bit more than 30. And we've got a mean of 5 and a variance of 8.33 divided by 50. Okay, just to put a little bit more sort of intuition into this, if we add two random variables, then the variance of that sum of two random variables is the sum of the variances. Okay, again, there's maths that supports that. So if we take n of the same thing. We're basically getting n times sigma squared. That would be the variance of that. Similarly, if we've seen this under expectation and variance, if we multiply a random variable by n, then the variance would be n squared times the original variance. Well, this is, we're not, our multiplier is not n, it's 1 over n, because that represents the process of taking the mean. So that's what we would do if we just simply had one, the single random variable, the original random variable, if you like, and divided by n, then that would be the variance. But what we're doing is sort of kind of a bit of a mashup of these two. And what we're looking at doing is taking the mean of n observations. So we kind of get the combination of these two things acting. So we get n, we've got an n multiplier up and an n squared divider, and that's going to give us that figure there. So that's not exactly a proof, but it just gives you a bit more intuition as to why that would be the case, that we get this sort of narrowing in effect. So let's have a look at a couple of examples. So this comes in a lot when we're doing hypothesis testing. This video kind of goes before the hypothesis testing. So at this stage, we're just not doing something quite as rigorous as the hypothesis testing process, but I think it's enough to illustrate what we're doing. Incomes in a certain town are strongly right skewed, so it's not normal, it's not uniform either, with a mean of 36,000 and a standard deviation of 7,000. So we don't know what the distribution is, but we do know what these two parameters are. A random sample of 75 households is taken. What is the probability that the sample mean is greater than 37,000? Okay, so that's our random variable there with some unknown distribution function. It's got a mean of 36. It's got a standard deviation of 7. When we're talking about the normal distribution, we always put the variance in there. So the easiest way to do this is that's 7 squared. And then this is our sampling distribution. So that basically says we take 75, and that bar at the top means we take the mean, and that's going to be normal distribution, near enough anyway, with a mean of 36 and a variance of 7 squared over 75. Well, that works out to 0.808 squared. So in other words, there's a mean of 36 and a standard deviation of 0.808. We need the standard deviation, don't we, to stick into our calculator. So what is the probability then of getting a test statistic which is greater than our 37? These are in thousands, obviously 37,000. So we can basically plug that into our calculator. Let's just do that. We've got that there. We're doing the normal cumulative. So that's that. We've got a lower of, well, we're looking at something greater. So what we want is our 37 is the lower, and the upper is something right at the far end. Do that. Our sigma is 0.808, and our mean is 36, and we've got a probability of 0.108. So the probability is 0.108 to 3 decimal places, and we would have to take a view as to whether or not that was an extreme kind of outcome, or whether it's does it support our ideas about the original distribution or not. Okay, so that is that one. There's another example here, which I think just do this one, and that should be enough for now. School children entering a sweet shop spend a mean of £1.50 per visit, with a standard deviation of 36 pence. £1.50. The shopkeeper puts all the prices up. I thought he'd be making the mint. But, the next 100 children spend on average £1.45. Has the price rise caused sales to drop? So to answer this, we're to determine the probability of observing a mean of £1.45 or less for a sample of 100. If the true mean is still £1.50, so we're saying, well, let's assume the mean is still £1.50. Is this just random variation that we've got this £1.45? But of course, it's an average. It's an average of £1.45. So the original distribution, we're saying that's X, and we don't know what distribution it is. But it's got a mean of 150 pence and a variance of 36 squared, because the standard deviation is 36. So the sampling distribution has got a that's what happens when we basically average 100 children. It's got a mean of 150, and well, we have to divide by 100, and that gives us a standard deviation of 3.6. So what, therefore, is the probability that this X bar would be 145, given that it's got a mean of 150 and a standard deviation of 3.6? And okay, well, I can pull the calculator out and put the numbers in again, but basically that will come to 0.082 to 3 decimal places. So that is how. Is that small? Is that small, or is that, you know, just random variation? I mean, it's not particularly small, is it? I mean, it's 8%. But you know, we may decide that's small enough for us to conclude that the price rise has caused sales to drop. And in fact, the conclusion I've put here is that it's unlikely that raising the prices hasn't reduced sales. So yeah, it does seem to be quite an extreme change. Okay, conclusion: raising prices has reduced sales, but not necessarily profit, of course. Okay, so that is that. So that is the sampling distribution. Very important, and it will come back around when we're looking at the hypothesis testing with the normal distribution. But hopefully that has made sense and been useful. I'll see you in the next video.